Yeah, g'day, and welcome back to this old bandsaw repair channel. Now last week I pulled the gearbox of my bandsaw apart because it was jumping out of gear. Big thank you to everybody who watched that video and especially those who commented, basically confirming that what I need to do to fix this is address this shifter mechanism, address the play in the drive to the shifter, and probably fix up the shoulders on the drive dogs. So let's get on with those repairs. If you haven't seen last week's video yet, hurry up and watch it because it'll make everything much clearer. Right, quick refresher. When I got this machine, it had a slogged out intershaft bushing, which allowed the output shaft to wobble around really badly. So badly that a woodruff key got released, got stuck in one of the teeth, and snapped it off. My mate Luke down in Malta saved the day by machining up a matching pair of gears to replace the broken one. Emil in Romania had them plasma nitrided for me, and then I could install them. So I put in new bearings, put it all back together, and the gears are now perfect, but it jumps out of gear. I thought it was jumping out of gear because I did a terrible job of regrinding the heavily worn mating faces of the drive dogs of the selector, but that's only part of the problem. The bigger issue was that I didn't understand this design. I thought that the dogs would stay engaged just by being engaged, but actually they have to be held into position by the shifter fork. And unfortunately this shifter fork is so completely worn out that it allows the selector to jump out of gear even when the fork's correctly positioned. So last week I asked you guys for some help with the troubleshooting of the system, and I must say I really appreciate all the feedback I got. Just to summarize, here's some of the things which came up. One, this shifter design has these two balls which should fit the slot, but these balls are under 1/8 of an inch and the slot's nearly 6.75 or so. Now I wasn't sure if this design with the two balls staked in place with a bit of peening was original or not. I got some feedback from a couple of DoAll operators that say that yes, this is a design which DoAll uses. However, it looks like this is not an original DoAll part. It's been probably shop made after the first one wore out or something. So even if the balls were in good condition, which they're not, they would still be very loose in that slot. You can also see that it's worn down a lot on this side, but not on that side. A 1/2 inch has been reduced to 10.3 millimeters. The second comment people made is this bad wear pattern through here on both sides, where it's obviously been contacting the shoulders of the selector. Now some of the motorbike guys said this looks like someone's sort of tried to force it. Maybe this joint's become bent, and looking at it, it's definitely not square. Although that wear could also have occurred when the shifter was running on the slogged out output shaft. Third thing that was questioned is, do we have a lot of wear on the shaft allowing the shifter fork to tilt in its guiding surface? That guiding bore is directly machined into the casting. While it does have a little bit of wear, it really doesn't seem that excessive to me. If I make a new shaft up, then I'll measure it with a bore gauge and make the shaft to fit. DoAll replaced this kind of ball guiding with a more conventional shifter fork. You can see here on the part sales from DoAll, they have just welded some sort of probably hardened steel slippers on there. And I also got a photo from Mike showing me a similar design. So considering the crappy condition of this one, I'm going to make a new shifter fork. Now DoAll would sell me one, but unfortunately their pricing's done using a system called EWD, equivalent weight in diamonds. So I'm not going to pay 570 bucks plus a ton of shipping and stuff from America for a piece of 5mm mild steel plate with a couple of features on it. I can do that myself, wasting probably $1,000 worth of time. So which design do I choose? Design A would be another 2-ball yoke. I think the second idea I would have would be making the whole thing out of bronze. I think C would be a sheet metal part with a brazed bronze wear surface. Let's just call it a slipper on each side. And my last idea, I guess, would be a case hardened steel part. Now what would you choose? So advantage of the 2-ball method, it's probably quite easy to make. 2 holes drilled, probably with a ball end mill not all the way through, and then drop in 2 balls and peen it. But I would need to find something like 6.6, 6.7 millimeter balls. I mean, there's probably some supplier that could supply them, but it'll take me ages to get them in. Plus, I think it's a crappy design because once you've dropped the ball into place, you then have to stake it or peen it in there, and that's going to cause a whole bunch of like point loads on the ball, and it's just going to wear out again too fast. I think I'm going to can that idea. This one, what I could do is just draw up the part in CAD, 3D print it, use that as a pattern, and then cast a bronze replacement part. And then it would just need one hole, just file to fit the wear surfaces to a really nice fit, polish them, and it'll be done. So that's quite tempting. I like casting. The third one would be to do it like DoAll now does it. So that's also quite tempting. Oh, that shouldn't be cast, that should be case. The third one would be to CNC machine a part out of thicker steel and then case harden it. Now the problem with this one is that my oven's currently dead. It's a two-phase oven, so there's two heating elements and both of them are burnt out. I could try splicing both of the heating elements, and if one of them worked, I should be able to get it to run for a couple of hours, however long it takes to case harden that part. That's also quite an attractive option for me. Right, so this is the oven I made. I'll leave a link up in the top right corner. Don't copy this design. It wasn't a good design. While this simple PID controller seems to hold temperature nicely, in practice you normally need temperature ramps for heat treating or for most other processes in the workshop, and it's a pain to have to babysit it and have to, you know, come down every hour and increase the temperature manually. So when I build another oven, I'll use some sort of controller where I can program in temperature ramps and profiles. Well, the calcium silicate board I used to make this thing has fantastic insulative properties. Unfortunately, it has like no mechanical strength whatsoever. Seems to be in pretty good shape where it hasn't been touched. All around the door, and especially on the door face, it's just crumbling and falling apart. Now the next problem I had was here I had a part fall over and short circuit this coil, and the other coil's really gone loopy and gone all over the place, short-circuiting itself. Not sure if I can even do much with that. Now when I built this, unfortunately I didn't really put any thought into maintenance, and there's really no way to simply replace the coils. Between the insulation dying and the coils dying, there's really not much point in trying to fix this oven. I need to scrap it and make a new one, but I don't have time right now. I'm kind of hoping that I can do a splice repair on this coil and get one more heat out of the thing. But the problem with this Cantel wire I made it out of is that it's really nice and ductile when unused, but as soon as it's been heat treated once, it becomes quite brittle and breaks easily. So what I'll be trying to do is just try hook into these two ends here. I'll use some fresh wire and just try and make a jumper between the coil and this location. Now, to be honest, I'm going to predict failure because this is already oxidized. When I wind new wire onto the old wire, there's probably going to be a reasonably high resistance joint which will probably overheat straight away and melt in that position straight off again. But hey, what have I got to lose? Okay, so that's already broken off. I honestly think that's a non-starter. I think as soon as I put any mechanical pressure on this to try and reconnect it, it's just going to snap and snap and snap. Right, no oven means no case hardening, so that kills that option. So do I do a bronze casting, or do I braze some bronze slippers onto a piece of sheet metal? So looking at my brasses and bronzes, I think I've got a bit of sheet under here that might be interesting. Right, so that brass is about 1 millimeter thick. So a layer of this either side of 5 millimeter steel would take it out to about 7, a bit above, because the silver solder would also take a bit of space. So that could work. Okay, so I went for a rummage, and this is the only piece of 5 millimeter steel I've got, which is unfortunately too narrow. To make a part out of that, I'd either have to go to the metal supermarket, which I don't really have time for, or I just chop off 2 pieces and weld them together like down through the split line or something. Yeah, I guess that could work. There shouldn't be any major loads on that. And then braze the bits on those sides. So at the moment option C is looking doable. However, I've never done any TIG brazing. I don't have any bronze brazing rod, and I don't have an oxyacetylene kit. But I do have a foundry. So I think I'll give this one a go. Let's start with a pad, make the extension pad, add a few fillets, put a little hole in the top because that's really nice for like a centering hole when I need to drill it out. And on the back I'll just put in a couple of alignment dowel holes. Right, then a couple of minutes in the toaster oven and we're all ready to go. Perfect. And here's my model. Unfortunately, the first one I printed out, I forgot to scale it by 2.5%, which is the shrink factor for bronze. So I had to print out a second one. One thing I really like about a modern printer like the Bambu Lab is that it prints so perfectly accurately that you can do like a alignment pin and it just fits. So I printed those 3 tiny little alignment pins. They're like 4mm diameter, 3 or 4, can't remember. Glue them in place. Now, given that DoAll's design requires that the shifter hold the selector engaged, there were a lot of comments pointing out, shouldn't there be some sort of detent system to hold it in place? And I went looking on the internet and I found that sure enough, DoAll did have a detent system on some of their other designs. So what I think I might do is add some sort of a bushing block onto this bracket to both take the slop out and guide the linkage better and also incorporate a detent into it. Now first up, that bracket's going to need a little bit of straightening. Okay, that didn't take much. So on top of the yoke that I'm making, I also printed up this block, which is going to be my detent block. I've done all my casting so far with water-bound sand, which is just sand, clay, and water. But a couple of years ago, a mate organised me this bag of oil-bound sand. Now, this stuff's like super fine. Doesn't really feel like wet sand. It feels more like window putty or kid's silly putty or something. But I've been kind of keeping this aside for a special project. Well, I guess it's time to do this special project with it. The material I'm going to be casting is bronze. Got a few billets of it here. I'll just need one for this job, I'd say. As it's such a small amount of metal, I think I'll just do this melt with gas. Turn that down a little bit till it gets stable. Now you might be wondering why I'm using such a ridiculously big riser. Now the reason for that is, one, I don't want that block to shrink too much, but the second thing is the riser, once I cut it off, will be a nice little bit of bronze stock that I'll be able to use to turn up bushings or something on my lathe. So that's the bottom. Just going to come in, run around. So I need some runners from here to there. Okay, so it looks like my gas is frozen up. I'm going to have to switch over to oil. I probably should have put that into a bucket of water. It's not that warm today. Now I don't want to get any air trapped in here, so I'll just put a couple of holes in it just to let the air come out. Ah, you dumb shit. I didn't weight it down. Okay, big screw ups there. The dumbest one was not weighting down the mold. Sand is much lighter than bronze, so I floated off the top or floated off the cope. The metal poured out the side. That's a real beginner's mistake, that one. The big chunk's going to be fine. The top half of this looks like crap, so I'll have to recast that. Since the furnace was already hot, the second melt went much faster, so I had to really hurry up and get that pattern molded up again. Right, let's shake out the other one. Wow. Don't know if you can see it there, but you can see the striations from the 3D printer. Okay, so what do these two castings tell us? Well, this was the bottom. This is the lower side, and you can see this block seems to have filled quite nicely. You can just see the striations from the 3D print on the top there. This was printed in PLA, this was printed in PETG, and I think PLA gives a slightly better surface finish. This is usable because it was only really filling the drag only in the bottom of the flask. It already filled, whereas you can see here, these bits started to fill up, but then the coat floated off, lifted up, and the metal, which probably already filled this area, flowed out over the side and destroyed the casting. But okay, I'll cut this out. This will be usable. What about the other one? So once again, this is the lower side. This is looking a lot better. There is a wee bit of porosity in there, or maybe inclusions. So maybe I didn't get my metal clean enough before I poured it. Now you can see how it's picked up the texture from the 3D print really quite nicely. And that's why you use an oil-bound sand. They're very, very fine sand grains and just pick up detail beautifully. Probably overkill for this part, but I wanted to try it out. Now the other side, which is the upper side, once again does have some inclusions and some, maybe it's air. I was planning to put some little air vents in it as well, but I forgot. Most of the strength is down around the thicker arms on the edges. It's not going to be the prettiest part on this side, but I'm kind of hoping it'll still work fine. Now in terms of dimensional accuracy, this should be 76 millimeters across. And it's about a half a millimeter over. In thickness, it should be 8. Wow, that's pretty darn close. Congratulations to Team New Zealand on another brilliant regatta. Also Ineos, top work, they'll be back. So that'll be the end of Glenn Ashby's brilliant sport reporting for a while.
Both teams having a short shift through their gearboxes, going from 3rd to 6th, then to 10th, and then back to 2nd again.
Emirates Team New Zealand win the Louis Vuitton 37th America's Cup.
2, 1. Beautiful, boys.
I'll need to machine it down because the slot here is only 6.75. Right, well there you have it. I'm pretty happy with that casting. Even if it does have a wee bit of inclusion and porosity, I think it'll still do a decent job. Big thank you to Bambu Labs for the X1 carbon printer, because that's brilliant for pattern making. With the much tighter layer lines, it's much quicker just to print the part and cast it rather than having to dick around trying to fill in striations and sand and bog and paint. So really happy with that. The other machining job's going to be, we'll be getting into this, mounting it onto the bracket, boring a hole through it, and making up a detent to go on the top. That should hopefully all be next week's video. Guess we'll see how far I get. Thanks a lot for watching. Catch you next time.